Yeah, sorry for the inconvenience. So let me start my presentation. Hello, everyone. I'm Yoonseung from Seoul National University and Yale University. Today, I'm going to introduce my work, VeriRT, which is an end-to-end verification framework for real-time distributed systems. Our research aims to formally verify safety-critical systems like autonomous vehicles, flight control systems, or power plant control systems. These systems are typically designed as real-time and distributed systems for the following reasons. First, they are required to meet real-time constraints for their safety and reliability. For example, an autonomous vehicle must detect and respond to environmental changes before strict deadlines. Also, they require distributed architectures to handle physical constraints, such as placing sensors and actuators in different locations. In our attempt to develop a new verification framework for real-time distributed systems, we have encountered several key challenges. So next, I'm going to introduce those key challenges and our solutions to address them. So let me start by outlining three key challenges. The first one is about modeling timing behavior. So it's about capturing how programs behave over time. The second one is about handling time computation dependencies. Timing and computation are mutually dependent so that they must be verified together, not separately at some point. And the third one is about reasoning about integrated, distributed, and real-time properties. So their combination multiplies system complexity. So we need to manage them in an effective way. So to illustrate the challenges, let's use time division multiplexing as our motivating example. In this system, multiple physical nodes share a single communication channel by dividing time into multiple slots. Let's consider a node that is assigned the grace time slot so that it may send a message only within this slot. And let me walk you through the program code of this node and the expected behavior of this code. We start from the top of the loop, and this circle in the center represents the program state at this moment. First, the program calls gen message, which takes some time to generate a message. Then, the node needs to sleep until the time slot begins. And to calculate the amount of time to sleep, it first obtains the current time by a system called getTime. The return value t will be between the call and return times. Then, based on the value of t, a function sleep time computes the amount of time to sleep, which is w, and it is calculated carefully by considering all time jitters and local clock skew. The next line calls the sleep system call, which will return after some time, which is approximately w. Then this makes the program call send within the time slot, and it returns within the time slot. Now, we described the first challenge, modeling timing behavior. In conventional untimed program semantics, an execution tracks only the event order, but not the timing. However, to handle real-time properties, we need to model the timing behavior of programs so that an execution tracks the timing too. And an observable event is paired with its occurrence time. So now the question is, how do we specify the timing in an execution? One naive approach would be like assigning maximum time bounds for each type of instructions and adding random time within the bounds for each transition. But however, this approach will not give a proper estimation on the actual execution time because compiler optimizations significantly change the code structure to reduce execution time. Therefore, we need another approach to model the timing. Then we explain our solution here. Our approach encodes timing assumptions directly in operating program semantics, rather than modeling timing from the code. And this lets us use these assumptions during verification. So the timing assumptions now become verification conditions that we validate against assembly code through worst-case execution time analysis or rigorous testing. Let me explain more details with our example. We will start from the time when the getTime system call returns. At this point, the timing assumptions specify the time-bound EST for the user code between the return of the getTime system call and the next call to the sleep system call. So like this, timing assumptions declare time bounds between a call and a return of system calls, or a return and a call of system calls, so that they are well defined throughout compilation from C to assembly. So based on the time bound, the semantics set a deadline TD, that is until the next call to sleep. Then the semantics may take some time to complete the user code, sleep time, and as long as the next call to sleep occurs before the deadline, the semantics updates the sleep system call as we did before when we set TD. And to rule out executions that violate the timing assumptions, our operational semantics generates a special event NB, which stands for no behavior, to mark these executions invalid. Then these executions will be discarded when we derive valid behaviors of the program. So in verification, users can leverage the timing assumptions by just assuming that there is no NB in the execution. So now, let's move on to the second challenge. The problem here is that we need to devise a new method for reasoning about timing and computational behavior together, since they are mutually dependent. So to demonstrate this, we will show first how a computational bug may cause timing spec violation, and then how a timing bug may cause computational spec violation. So let's go back to our motivating example. The current figure describes a correct execution where the call and return of the send system call are within the time slot. Now, let's suppose that there is a computational bug in the sleep time function. Then, if the sleep time calculated a value that is too short, then it might send the message before the assigned time slot. So in this case, this execution might still generate correct computational results, but obviously it breaks the timing specification regarding the time slot. Now let's suppose that a timing bug occurs so that the program called send too late. Then the destination node may receive the message at a time that is not intended by the system design. Then this mismatch between the received time TR and the message content M, the node may generate abnormal behavior that violates the computational spec. So to address this challenge, we designed a set of new simulation relations named timed simulation relations. The first one is program local simulation, which is just a standard simulation for matching two program states. This simulation is useful when you want to apply time-independent reasoning to abstract away code-level computational behavior. The second timed simulation is node local simulation. And Yeah, this allows reasoning about timing and computational behavior together at the node local level. So at the high level, the simulation works as follows. So in verification, you can assume that identical messages are coming with the identical timing from the network to both source and target node states. Then you need to guarantee that the source node can simulate target node's behavior in terms of the content and timing of each outgoing message. Third, you design the global simulation that can handle global properties by reasoning about both time and computation. This simulation relation remembers a piece of observable trace, which is useful when we want to eliminate non-determinism regarding execution time. And this will be discussed later in the case study part. So our last challenge is about reasoning about integrated, distributed, and real-time properties of systems. The combination of these two properties multiplies system complexity through their non-determinism. So let's see what sources of non-determinism are present on each side. First, regarding real-time behavior, the execution time of program code and system call are non-deterministic. Also, each physical node in the system has its own local clock with individual skew. And second, regarding distributed architecture, the network communication has non-determinism in message delivery time, drop, and duplication. Also, there are non-deterministic interleaving between the nodes, physical nodes in the system. Therefore, we need a method to manage these complexities effectively. Our solution uses layered abstraction to manage complexity. Instead of handling everything at once, we separate concerns into layers and reason about each layer independently. As this diagram shows, we gradually abstract away the complexities we mentioned in multiple steps. So building on these solutions, we developed VeriRT, a verification framework for real-time distributed systems. And as case studies, we applied this framework to verify two application systems. This is the overall structure of the framework. It supports the end-to-end verification from an abstract global spec down to the assembly level. And the framework adopts layered abstraction, and each layer is facilitated by applying a proper timed simulation relation. So let's start from the bottom layer. For C programs given by the user of the framework, our framework provides formal guarantee that the behavior, the whole system behavior is preserved until the assembly code if it's compiled by CompCert. This is done by proving a lemma in the framework that says the generic simulation relation of CompCert implies our program local simulation. So we named our extension of CompCert, CompCert RT, which runs the whole translation sequence of CompCert 3.9. In the upper layer, we can abstract away computational behavior of programs against their computational spec. So at this level, the user can apply program local simulation technique to merge multiple steps of the concrete program semantics into one single abstract step in the spec. So we can significantly reduce the number of interleaving as a result. Then we can further abstract away node local properties by applying the node local simulation technique, which reasons about both timing and computation. So in particular, at this level, we can eliminate local clock skew, which is managed by the OS model. And next, the framework provides global simulation to reason about global properties, such as message delivery times of the network. And the user can freely create additional layers for handling more properties, such as execution times. We conducted 2 case studies. The first one is Parseware, which is a middleware program that implements a communication protocol for real-time distributed systems. Second, we verified Christian's algorithm. This is a clock synchronization protocol for distributed systems with a server-client architecture. So in this talk, we will focus on the first case study. Parseware is a middleware that implements the parse protocol. The protocol assumes a physically asynchronous environment, and it provides a logically synchronous view to its application layer. Let's see what an asynchronous system looks like. In this figure, there are 3 control units who communicate through the network. And each job is driven by asynchronous message delivery that causes non-determinism in the system behavior. Then let's see what a synchronous system looks like. In this figure, the message delivery happens a periodic and deterministic way. So this eliminates non-determinism, which makes the system easy to design and verify. And in this slide, I'm going to show how to deal with the asynchrony in verifying Parseware. So first, let's revisit our global simulation. This simulation relation remembers trace for realigning events. Let's see how we used this to verify synchronization. This is an execution generated by the system model that still maintains non-determinism in execution times. Let's start by matching our initial state with an empty trace. Then, in verification, we can let the target proceed while the spec stays still. And the trace generated by the target is accumulated in the relation. Then, when the target execution has proceeded enough to match the next state of the spec, we choose a step of the spec that can generate the identical trace with the accumulated one. Then we can resolve the accumulated trace, and we can do the same for the next period. So in summary, to handle real-time and distributed behavior, we have addressed 3 challenges, and we use our solution to build the VeriRT framework, which supports end-to-end verification. And on this framework, we verify 2 application systems. So that's it. Thank you for listening.
Thank you. Okay, we will take 1 question. All right, if there's no question, let's go to the break. Thanks, speaker again.